Hello everyone, welcome to the latest COAV webinar. Today we're going to be talking about sensors. My name is Alex Spitzer and I'm on the software sub-team for COAV. Let's get started. All right. So first off, before we get started, if you have any questions during the presentation, definitely email me at aes368@cornell.edu. At the end, I'm going to give some time for questions, and if you send any emails, I will look them over and answer them at the end of the presentation. All right. So sensors. What are sensors used for? Well, sensors are used to perceive the outside world. Humans have 5 senses like hearing, eyesight, touch, smell. I don't really remember the 5th one. But submarines have other types of sensors such as cameras, which are visual sensors, velocity sensors such as a DVL, sonar, pressure sensors to measure depth, as well as accelerometers, gyroscopes, and magnetometers. Today, we're mostly going to be focusing on the last group of things, accelerometers, gyroscopes, and magnetometers. You could break the sensor problem down into kind of 2 areas, position and orientation. You want to be able to know accurately your position in the world, which is a 3-dimensional world vector, as well as your orientation, which describes which way you're facing and how much your pitch and roll. Why? Why is knowing your vehicle state, why are sensors important? Well, knowing your vehicle state is very important. In particular, your heading and velocity. If you know your heading and velocity, you can integrate the velocity with your heading to get position. And knowing your position is very important because it helps with localizing mission elements and knowing where to go next. So your vehicle state can be broken down into 4 things. Position, velocity, orientation, and angular velocity. Now, how can you estimate those? Well, in theory, if you have accelerometers and gyroscopes, that should be enough. The theory behind that is you have 6 numbers, so 2 vectors, and you have 6 degrees of freedom. 3 translational degrees of freedom and 3 rotational degrees of freedom. Unfortunately, that doesn't work so well because a lot of those measurements are very noisy and they don't give you as accurate results as you would want. So you need some sort of way to measure absolutely your velocity and orientation. One of these units is called an ADCP, which is an acoustic Doppler current profile, most popularly known as a DVL. So this tells you your velocity based on sonar that is reflecting off the pool floor or ocean floor or even the ocean surface. So that's very useful if you want to measure your velocity. If you don't have a DVL, you can rely on visual cues. And this relies on having a very well parameterized camera that you can use to kind of determine how fast you're moving and where you're going. All right, accelerometers. Accelerometers measure acceleration, as you might have guessed. They measure something called proper acceleration. What's proper acceleration? Well, proper acceleration is a fancy term that basically means that accelerometers measure, in addition to any linear acceleration on them, the Earth's gravitational acceleration. So in most standard units, you can think of them as 3 orthogonal springs that are that respond to any accelerations. So if you have a spring and you accelerate it in one direction, the spring will compress, and that will be an acceleration reading. What's cool though is if you rest the springs down on the floor, there is a normal force from the Earth pushing them up to prevent them from falling through the floor. Just like there is a normal floor pushing me up, preventing me from falling through my chair right now. So that spring that's being compressed as the accelerometer is resting on a surface measures Earth's gravitational acceleration, which usually comes out to be around 9.8 meters per second squared. So that turns out to be actually very useful in determining orientation, because you can ask the question, which way is the gravity vector pointing? And if it's pointing in my z-axis, I'm probably not sideways, right? And if it's pointing in the opposite direction, I'm probably upside down. So, however, that requires a simplifying assumption, namely that there are no actual accelerations in the accelerometer. Because consider the following 2 cases. You have an accelerometer that's sitting upside down on the surface. So it's experiencing a negative 9.8 acceleration. and its z-axis. Case 2 is you have an accelerometer that's right side up, but accelerating upwards at 9.8 meters per second squared. So from the point of view of the accelerometer, there is no difference in the measurements it is receiving. So you have no way of disambiguating between an accelerometer resting on the surface upside down and an accelerometer accelerating upwards at 9.8 meters per second squared. However, fortunately, autonomous underwater vehicles usually don't go shooting through space at those kind of g-forces. So this assumption is reasonable in that we don't experience prolonged sequences of high g-forces. However, it's something to keep in mind, as you're probably thinking you should use accelerations to calculate calculate your velocity. But if you're using it for orientation, you should keep in mind that by using it to calculate orientation, you're essentially saying this is useless in calculating velocity because there are 0 accelerations on the vehicle, which is not true. Of course, we move through the water, so there are accelerations. The problem is that accelerometers are usually very noisy, and they don't lend themselves well to estimating your velocity. We're going to talk more about that later. Gyroscopes. So the second element in most units today is gyroscopes, and those measure angular velocity. You have RPMs, radians per second, whatever units you want to use. And you can think of it kind of as the spinning top in that picture. It stays up because there are forces that are counteracting gravity's torque to pull it down. And there are small electrical sensors that can be used to detect this force and determine how fast something is rotating. The interesting thing about that is it can also be used to derive orientation, much like accelerometers can be used to derive velocity. You simply integrate your velocity and you get your angle. And then the interesting thing is you can combine them with accelerometers to kind of get a nicer reading of orientation. If you have two sources of data, they both complement each other, and you can compare the two and see if they match. We're going to talk more about sensor fusion later, but this is one way in which two elements can be used to estimate the same thing. And they both have different properties. For example, accelerometers are very noisy, whereas gyroscopes have another problem, namely they drift. We're going to talk more about that later. One thing to keep in mind is gyroscopes usually have something called gyro gain, which is a steady state offset to their reading. So even when they're standing still, they probably measure a small amount of angular velocity, and you can calibrate against that by keeping the unit still and capturing these constants and simply subtracting them from the readings when you're actually rotating. The last unit of core sensor bits that we're going to talk about are magnetometers. And these do exactly what you think. They measure the magnetic field surrounding them. So what's cool about that is they're actually, just like accelerometers, 3 orthogonal axes. So they give you a 3-dimensional vector that is the magnetic vector around at that point. So as you know, the Earth generates a magnetic field coming from the poles, and it's been used for navigation for centuries. So not surprisingly, autonomous underwater vehicles also use the same magnetic field to get an absolute measurement of heading. So this vector that's coming in from the poles kind of has a direction, right? And that direction is parallel to north-south, or however you want to think of it. And depending on the X and Y readings of your vector, you can determine which way you're facing in relation to north, which is really useful. But the issue really with these sensors is that they're also susceptible to magnetic interference and distortions of the surrounding magnetic field. So one of the weaknesses of using just simply magnetometers to measure heading is that it's noisy, and it's also susceptible, like I said, to noise and metallic disturbances around it, and obviously other magnets in the area. We're going to talk more about that later. It's important to calibrate for those anomalies so you have the most accurate magnetometer readings possible. So you might have heard these terms like a 9-axis IMU, 6-axis AHRS. What does that really mean? Well, let's start with the definitions. IMU is an acronym, stands for Inertial Measurement Unit. AHRS stands for Attitude and Heading Reference System. Attitude is another word for orientation. So both of these kind of attempt to give you a measurement of a system's orientation. In general, IMUs are kind of simpler systems that don't do too much onboard processing, whereas AHRS provide a full solution, and they usually have a complex microcontroller that has some type of onboard filtering that fuses the 3 outputs of accelerometers, gyroscopes, and magnetometers. So where does the 9-axis part come from? We live in a 3-dimensional world, so obviously there aren't 9 dimensions. Well, accelerometers have 3 axes, gyroscopes have 3 axes, and magnetometers have 3 axes. So 3 times 3 is 9. So the kind of saying is you have 9 axes, 9 degrees of freedom, 9 different readings you're using. There are also 6-axis units out there, which usually combine accelerometers with one of the 2 other sensors. So accelerometers and gyroscopes are really nice for orientation, as well as accelerometers and magnetometers. So yeah, most of those units give you the outputs of the individual accelerometers, gyroscopes, and magnetometers. And if they have a microcontroller on board, they probably do some kind of onboard processing that can filter the output for you and provide some kind of orientation solution that is hopefully more accurate than using the raw data. And the processing these things do can range from simple trigonometry to fancy sensor fusion algorithms like Kalman filters, which we're going to talk about later on. So you may be wondering, well, I have my gyroscope data. Why can't I just integrate that and then there's my orientation? Boom, I got it. Well, in theory that works great. Math is you integrate the velocity, you get your position. The first problem with that is you need a reference orientation. So you start integrating, you add that plus c term in the integral. You need to know what your starting point is, which is not a big deal. You can say, okay, whenever I start, I'm going to be at 0 orientation. That's not a big deal. The real problem with integrating noisy data is that the error quickly grows so massive it's not even worth doing. And to give you a little bit of intuition as why that's the case, you can consider a random walk. So you're at the number line. Consider a one-dimensional random walk. You're at 0, and every time step you make a random error in one direction. Let's say you make one error in the positive direction. The probability of you making another random error in the positive direction is still the same. You're not more likely to make an error back towards 0. You're still at the same state. So you might as well be 1 away from your desired value. And in fact, there's a theorem that says in one-dimensional random walks, every single integer is crossed an infinite number of times given enough time. So that kind of gives you an intuition as to why these things can quickly diverge. And that also assumes perfect integration. And that's impossible in practice because you have a discrete sampling of the signal. So quickly, you realize that if you kind of get diverging estimates of the position or orientation or whatever. Gyroscopes aren't particularly bad because they're not as noisy as accelerometers, magnetometers, but they don't. If you want to do it for heading in particular, it gets you can see the drift very quickly. So absolute measurements are very important. The best case is you have a GPS. In positions, as an example, you have a GPS that tells you where you are. There's no integration there. You know where you are. It's really nice. But unfortunately, that doesn't work underwater. So when we're building an autonomous underwater vehicle, we can only use that when we're very close to the surface. That's not ideal. The next best position is the DVL. So that provides velocity. And it's not very noisy. So you can integrate that velocity and get position. For orientation, we have magnetism. So that kind of gives you which way we are relative to north. So that gives you your orientation. It gives you absolute orientation in the surface plane, which is kind of the northeast, west, south plane. And then if you want to know your orientation in the up and down plane, gravity also gives you an absolute orientation. You can look at the accelerometer readings and ask, which way is the gravity vector pointing? If it's pointing straight down, well, I'm not pitched and rolled. If it's pointing in some other direction, I can do some trigonometry to figure out where exactly I am in relation to down, which essentially gives you your orientation. So one question of when considering these sensors is where. So you have these raw sensor values, accelerometers, gyroscopes, magnetometers. What do you do with them? Well, a lot of the fancy sensors do the processing on the sensor itself in the firmware. So that can range from simple math to a lot of fancy algorithms and fancy firmware. Many of those units are expensive just because they have complicated algorithms like extended Kalman filters and quaternion math, and a lot of times you're paying for the filtering that is done on the sensor. You don't have to worry about it. You just plug it in, you get your values, and you have a nice thing. You don't have to worry about it. You can assume certain things about it, like its accuracy and its convergence and stability. In addition to the firmware, some of the higher end units may also have better, fundamentally more accurate accelerometers, gyroscopes, magnetometers. So pay attention to the data sheets when you're considering a cheaper unit, which might have not only the lack of firmware, but actually units that have poor performance in terms of raw capabilities. The alternative to doing the processing off the sensor on the sensor is doing it on the sensor in your software system. So you'll get the raw sensor bits, raw sensor data, the accelerometers, gyroscopes, magnetometers. You'll extract those out and do whatever you want with them in your software system. So you'll do some kind of fusion and estimation there. So the advantage of that is you have a lot more control. It's obviously you have a lot more freedom in whatever you want to do. It's a lot easier to iterate, especially if you're running on a standard Linux system. You can quickly try things out and see if they work. So you can range anywhere from the high-end options, which is just buying everything, like a DVL, an AHRS. It does everything for you, and that's obviously works very well. You have a position that is tracked by integrating a DVL velocity, and your AHRS gives you orientation with some kind of onboard filtering that kind of uses its raw sensor data to filter the data for you. The problem with that is sometimes the firmware on these sensors can get very complex, and it can produce lag and effects that you really don't expect. And you think it should work better than it is, but it's really not working. In that case, you should play around with the settings. There's probably something wrong with the way it's configured. And again, it's not as easy to play around with that because it's a firmware and you have to deal with their idiosyncrasies of their communications protocol, whoever you're communicating with the sensor. Like I said, the alternative to that is doing more of the orientation processing off the sensor, which is doing in your software system. So that's ranged all the way down to just getting raw data to kind of a combination of some sensoring, some processing done on the sensor, in the software system. So for example, for UAV, we don't use the full AHRS. We go for a simple IMU, which we then input into our own common filter on board the computer, which we use to fuse the different readings from the IMU. We're going to talk more about that later. Another key point to consider is system compatibility. So different sensors, depending on your power constraints or communications constraints, you need to make sure that your sensor can be integrated to the system without much difficulty. So if you don't have a DVL for velocity measurements, position is actually very difficult. One of the things you could do is use visual cues. You can do visual servoing. If you don't have a DVL, you probably realize that it's very hard to stay still because you don't really know how fast you're moving. Sure, you can integrate your thrusters, you can integrate your accelerations, but like I said, that's prone to drift. So if you have a visual cue, you can look at the camera and say, okay, well, the object in the camera is moving, so I'm probably moving. So to stay still, I can do some kind of control that visual servoing, what's called, so you can kind of remain stable that way, and it's actually really important. It's also nice to be able to fully characterize your cameras so that if you see an object in frame, you'll know exactly how that corresponds to the world's position of the object. And that can help with not just velocity estimation, but other things like localization of objects and localization of the sub itself. A lot of fancy localization algorithms like SLAM and other cool robotic algorithms use camera and camera extrinsics and intrinsic matrix to use the visual data as efficiently as possible. So you selected a sensor, and now you want to integrate it into your system. The first thing you want to consider is the placement of the sensor. Sensors have magnetometers, so you want to stay away from permanent magnets and anything that generates a magnetic field because that's going to interfere with the sensor measuring the Earth's magnetic field, which is what we want to measure to see where north is. So as you know, current generates magnetic field in outward radii from the current source. So if you put it near the CPU, that might not be a good idea. Electric motors also contain strong magnets, so you want to keep the sensors away from your thrusters because that might cause an overwhelming amount of influence. In fact, one of the problems we had on CUAV was one of our sensors was right next to the motherboard of the computer, and it turned out that whenever the CPU was under heavy load, the heading reading on our compass would change. That was really bizarre. We're like, what's going on? Why is our compass changing like that rapidly? And it turns out that our CPU was oscillating. So then we figured out, oh, this sensor is really unusable in its current position. So we ended up putting it in a sensor boom. And that's a thing we have that's elevated from outside of the hull and is away from any kind of wires with large current or magnets or interference. So if you have a lot of stuff going on in the hull, it may be a good idea to consider dedicating an enclosure particularly for this purpose, namely a sensor boom. You want to keep that away not only from the wires, but also from the thrusters. Another point to consider is the communication of the sensor. Most sensors support RS-232 serial communications, and you can feed that through a USB hub to your computer. And depending on the type of sensor, depending on the company, there are different ways to interface with the sensor. Has a microcontroller, usually implements some sort of serial protocol. And implementing serial protocols is never really fun. It's just a lot of, low-level manipulation of bits and bytes and just doing the work to make sure it works. Usually we use C to implement that, but a good option is also Python. The PySerial module works just as well, and it kind of provides the nice things that Python provides in implementing that. If the sensor you're getting provides an SDK, that's definitely a plus, because then you just have a method like get me accelerometer data and it gives you the data, which is awesome. You don't have to worry about sending bits across the serial interface. Some even smaller sensors that don't have microcontrollers, you might have to do some kind of custom electrical solution, kind of a dedicated board to interface with it. And it really depends on what you're buying. So check the data sheets, check the specs, and like I said, SDK is a plus, which is nice. So a lot of sensors have different options in output. So usually 100 hertz is more than fast enough. You don't need to get data faster than anything you have that's consuming it. So if you're outputting at 300 hertz, but your onboard mission is only reading that at 50 hertz, that's kind of a waste of energy and time. There are two different options in how the data gets from the sensor to the serial interface, whatever you're using to talk to it. And that's really only an option for kind of sensors with microcontrollers on them, which is what we use in UAV a lot. There's polling mode and continuous mode. So polling mode, it's every time you ask the sensor, oh, give me data, get the data, give me data again, get the data. So that kind of obviously has communication overhead, but it's a little simpler. Whereas continuous mode is like, okay, start sending me data, and the sensor continuously sends bits across the wire, and you just read them without actually telling the sensor anything. Usually, the communication overhead from polling mode is not a big deal. So I don't think it matters too many which one you choose. Just be aware that if you're sending continuous mode, it may be difficult to. You need to make sure that the sensor state is clean when you shut down the vehicle, so that when you start it up again, you don't get a blast of data and you have trouble communicating with the sensor. Sensors can output data in a variety of formats. Euler angles usually the ones people go for. They're very simple, but they have lots of problems. We're going to talk about that later. If you can, you should use matrices or quaternions because they have nicer properties. Ideally, your entire system is based on kind of what matrices or quaternions. We're going to talk about that more on the controller webinar, which is on November 29th. Stay tuned for that. Another thing I want to mention is that some sensors have difficult communication interfaces. So, like I said, if you have an SDK, it's definitely nice because then you can just say, okay, set the continuous mode, set the format without without reading complicated protocol diagrams and figuring out how to talk to the sensor. Okay, let's talk a little about calibration. So one of the things you have to calibrate is gyroscopes and accelerometers. And like I said, gyroscopes have this thing called gyro gain, which is kind of a steady state value even when the sensor is not rotating. So just to calibrate for that, you just keep the sensor still. It captures this constant and it simply subtracts it from any readings in the future. So usually sensors have this option. You send it a gyro gain capture, and it's going to tell you, okay, sit still for 20 seconds, capture that, and then after that, all your gyro readings should be zeroed when you're standing still. Similarly, accelerometers have the same deal. There might be some steady state, so you have to capture the gain. And the local gravity vector might be different from the factory, or I need to calibrate that. So to do that, you keep the sensor flat, so it tells you where gravity is, and then it knows that that's the z-axis. And again, different sensors have to do this in different ways. Procedures. Most of them is just similar, just sending the command is different. So one of the hardest things to calibrate is the magnetometers, simply because they have a lot of ways to interfere in the stored magnetic field. There are two types of calibrations for the magnetometers. You have hard iron calibration and soft iron calibration. Hard iron interference refers to permanent magnets around the area. So if you have a permanent magnet, obviously magnetic field that the magnetometer is going to pick up. And that interferes with the Earth's magnetic field, right? So if you have an Earth's magnetic field coming in and something else coming in, that's going to offset the heading. And that's actually because that just that kind of manifests itself. And if you take circular around a circle, you'll notice that the center of the circle is offset by this hard iron interference. So the way you calibrate for that is you'll take readings and then calculate the center of whatever either the circle or the ellipse, which is also some soft iron interference we're talking about later. The center of this circle, and then subtract. Essentially accounted for this hard iron interference. And you usually don't have to implement this. A lot of sensors do this for you. They tell you, okay, spin the sensor 720 degrees. It takes these readings for you. And of course, if you have moving permanent magnets, that's for because it changes with respect to time. So you calibrate for ones, if they move, obviously something's different, so it's not going to be accurate anymore. But if you know when the magnet is in a particular position, you can kind of characterize that and deal with that accordingly. That's a little more complicated. But if you have a knowledge that, say, your actuator system uses a lot of magnets, and when you fire an actuator, something suddenly changes, a magnet left the vehicle. You can have some logic in there to say, okay, I fired a magnet. Now let me use this calibration profile for my sensor. That's something you can do. Soft iron interference is a little bit trickier to deal with because it's actually caused by changes in the magnetic permeability of the element. So air has a certain magnetic permeability, and if there's nothing but air around the sensor, everything's fine. But if you have elements like iron and steel, they have a much, I think it's lower magnetic permeability, or higher. They're more permeable to magnetic fields, so they kind of distort the surrounding magnetic field without actually producing a magnetic field of their own. So what that manifests itself is the circular readings that you expect to get end up being skewed. So you end up getting a kind of an ellipse instead of a circle. And to calculate for that, you actually have to characterize this ellipse and calculate the coefficients of its major and minor axes and undistort back into a circle. And usually, again, sensors will do this for you. They might demand some kind of more rigorous calibration process, such as painting the sphere, which means you have to point the sensor at every single possible 3D orientation, which is actually not feasible if you have a large autonomous underwater vehicle. And of course, you want to be doing all these calibrations in the vehicle itself. If you do it outside the vehicle, that's not very good because when you put it inside the vehicle, everything changes. So yeah, like I said, hard iron is really an offset to the magnetic readings. It's easily compensated for. Soft iron skews them. And it's usually less of a problem, but definitely hard to deal with. Like I said, yeah, most of them definitely come with software suites to do this. The problem with that is it's kind of frustrating that a lot of them exclusively run on Windows. So it's like, oh, I have this Linux system and I want to calibrate my sensor and I have to do it all manual with my sensor twiddling and bits over the wires. Serial communications. If only I could have a Linux version of this calibration suite. Well, most sensor companies don't do this. What you can do is actually kind of, if you don't have a Windows computer, you can actually pipe the sensor values over the network to another computer using something called USB IP, and then do that way. Whatever works for you. Just definitely keep in mind it might be more difficult than you think to calibrate these things, especially when the company that you're getting sensor for expects you to use Windows and provides support for Windows users. So you do it once and forget. But if things changes, you definitely want to recalibrate. If you add a large component in the sub, recalibrate. If it's metal, obviously recalibrate. If it's a magnet, definitely recalibrate. If you change location, the magnetic field obviously changes because you're in a different spot on the Earth. Your declination, the declination of the magnetic field is going to be different. So you should recalibrate. And what important note is when you're calibrating, obviously stay away from hard and soft iron, stay away from magnets, stay away from steel tables, because when you put the sub in the water, that table's not going to be there, and your calibration is going to be a little off. So yeah, like I said, complete soft iron calibration, maybe a little bit whether your sensor simply doesn't have that option on board, or you can't really rotate the sub in circles in the air unless you have like 10 people carrying it or something. So this may lead to problems such as non-linear heading. We call it non-linear headings, but it's really non-circular headings. So like I said, the magnetic readings get skewed into an ellipse. And if you look at this picture, it's kind of, maybe it's difficult to see, but the sensor will tell you you've spun 45 degrees, but really you've only moved like 30 degrees. So some of the readings bunch up in a certain kind of cusp of the ellipse, and then the other readings spread out. So some readings are faster than others. And that's not good, right? Because if you want to draw a box, you want to move in a box pattern, and you trust your IMU, you're going to end up doing some kind of rhombus because your angles aren't really 90 degrees. One simple way to correct with that, and this is actually something we do on CUV, is we just kind of take samples in intervals of 10 degrees in heading, and then match up what the actual heading was to the sensor reading heading. And then we keep this giant lookup table of all these headings. And then when we actually run this thing, we give it a sensor reading, and it matches the actual heading that's close to that sensor reading. So in a way, we're kind of undistorting this non-circularity in the headings. So you find the one that's closest to, and then interpolate between the two. And usually we do this on this circular kind of round-robin table thing that tells you the actual heading, and then we read the sensor data. It's usually an involved process, but it's definitely worth it. We can see the differences when we do 90-degree turns. They end up being more perpendicular than without this process. So this is kind of, it's a very simple way, and I'm sure there are more complicated ways, but this. Okay, let's talk a little about sensor fusion. So simple sensor fusion thing you do is basic stuff like you do a low pass filter or a median filter or an averaging filter. And our data, things have low jerk. Jerk is the third derivative. So acceleration. Usually any type of high frequency components of your acceleration signal are probably noise. So you filter those. That's a little bit of a higher acceleration, but not as high as the noise you see. I'm sure you've seen the sensor readings that they're just up and down, a lot of noise. That's a simple thing to do. More complex things you can do is something called a common filter, which actually used extensively in these fields. So let me give you a simple example of how that works. You have an IMU that it's not an AHRS. It doesn't do any fusion for you. It just outputs heading, which it computes from the magnetometer. And it also gives you the heading rate, which is computes from gyroscopes. So, and you want to use that to figure out your heading. So the heading is way too noisy. It's kind of, it's doing, like the accelerometer is doing this back and forth thing. It's just bouncing back and forth. But the gyroscope is not that noisy, but it's also subject to drift. Like we said, integrating it, it's not going to produce the results you want. So one option we can do is, okay, forget about the gyroscope. Let's just do a low-pass filter on the heading data. Yeah, that's cool. It might be a little less noisier. Probably going to work okay. But the sad thing about that is it doesn't actually use the gyroscope data. If you have data, you might as well use it. It's an independent source of data. So it's something that you should take into account. Why don't we just average the result of both? So what I can do is I can take my measured heading for my magnetometers and integrate my heading with the gyroscopes, have two results, and take the average of the two. Yeah, that's okay. It's kind of assuming that both are equally correct, so it's not that okay. We can do something better, and the common filter actually does this. This is kind of a simplified version that I'm going to show you. It's just a one-dimensional variable and its derivative. So if I don't know if you know anything about the common filter, definitely check out Wikipedia pages on that. It's very cool. But essentially, it can be broken down into two steps. You have your predict step and your correct step. So that's kind of similar to what we're doing here. We have a prediction, which is we're integrating our gyroscope, or integrating our heading rate. We have a correction, which is the new measurement from the magnetometers. So our prediction step is simply our next heading is the current heading plus the heading rate times, this is just integration, times the time since the last heading was measured. And that gives you some heading, and in case number one, where we just use the heading, that's what we'd use. But to correct this, we're going to actually, the common filter equation reduces to this first line here, which is you use the measured reading, subtract the difference of the measured heading and the predicted heading, and multiply it by this thing called K. K is the common gain. And this gets recomputed in kind of the equations I didn't show here, probably because I don't understand them, but they kind of use the noise covariances of the different readings and processes and to try to compute an optimal value of K. So if this looks very similar to linear interpolation, it actually is a linear interpolation between the measured heading and the predicted heading. And the measured heading, of course, is just the magnetometer heading, and the predicted heading is just the gyroscope heading. So if you see, this is kind of a generalization of the averaging we're talking about with K equal to a half. If K equals a half, this is just average. The idea why this is better than average is this K gets recomputed by the common equations at every time step. Something people error optimal in the mathematical sense, which you can check out by reading the Wikipedia page on common filters. And yeah, the result that comes out of this is smoother than heading data and does not suffer from drift because you have this update from the magnetometer that kind of keeps you on track. It's the best of both worlds. It's great. It's awesome. It's really cool. And of course, if you go into higher dimensional common filters, these equations become much more complicated. essentially there's a bunch of linear matrices. Let's see a little bit of that. So yeah, sure, we can fuse a variable and its derivative. That's cool. And we actually do this a lot. This is our primary filter for heading on CUAV. We take in a heading rate and a heading, and we pass through a common filter, and that's been working pretty well. But what we really want to do is estimate orientation. Fuse all 9 axes that we get from our accelerometers, gyroscopes, magnetometers. The common filter, the traditional common filter, assumes a linear model. That doesn't really hold. It holds up for the variable and derivative case, but we want to estimate orientation because it's nonlinear. You have kind of a sphere plus a little more, a fourth dimension. You have a sphere of possible things. Sines, cosines, circles are not linear. So there are extensions to the common filter called, the extended common filter and the unscented common filter. So the unscented common filter solves this problem by using the Jacobian matrix of partial derivatives and linearizing about the state. So that's actually used extensively. Read a lot of papers on that. It's been called the de facto standard. It's really cool. But something better you can do is called the unscented common filter, which actually captures nonlinearities to the third order using a particularly optimal chosen set of sample points around the state. And those are transformed through these matrices, and you have all this cool math. And it's used very well for orientation estimation. So what's the state for such a common filter? Usually it's a quaternion plus an angular velocity vector. You have your 4-dimensional quaternion and your 3-dimensional velocity vector. And the predict step looks similar to the previous case. You just integrate your angular velocity vector to get a new quaternion. You're probably wondering what quaternions are. This next slide is going to talk a little bit about that. Orientation, another word for orientation is attitude. You got 3 degrees of freedom, 3 dimensions in the world, 3 different rotations you can do. The most efficient way to represent orientation is, which kind of give you 3 angles around 3 axes. So that's your heading, your pitch, and your roll, or a rotation vector. That's just an axis, and its magnitude represents how much you're rotating about that axis. In fact, there's a theorem, which we're going to talk about later, which is tells you that any orientation can be described by a single axis and a single angle. A long time ago. The problem with orthogonal angles is they suffer from gimbal lock when you have rotations that. So, for example, when you change pitch and then rotate this pitch and roll, axis was then my my roll axis and the heading axis become the axes and coming out of the stub and heading axis. So that's not cool. And there is some singularities in the math which you should avoid. Matrices, they're nice, but they also have 9 numbers, so a little bit redundant. What usually people go for is quaternions. We actually use this in CUAV, and they're very hip and cool. Industry standard, apparently. There's just 4 numbers, 4 vector that is used to capture orientation. A vector of unit length vector. So quaternion is a way to encode this axis angle representation into a 4-dimensional vector. Those should be thetas, those boxes. They're not boxes, they're thetas. So if you have an axis with 3 components, Vx, Vy, Vz, a quaternion has 3 imaginary components, which we'll call Q1, Q2, and Q3. And to get those imaginary components, you multiply the vector, the axis, by the sine of the angle around that axis divided by 2. And the scalar component of the quaternion, which is Q0, is just the cosine of that angle divided by 2. It's very simple mapping, but it leads to very powerful objects called quaternions. And it's just a 4 vector. We limit them to unit length because, like I said, there are 3 degrees of freedom. And if we give it 4 degrees of freedom, you have an infinite number of things that map to a certain orientation. If we limit it to unit length, that gets rid of a degree of freedom or a back degrees of freedom for The cool thing about quaternions, as opposed, so you may be wondering, why not just use a rotation vector? I have a vector that's encoding my rotation and axis angle. That's good, right? Well, the power that quaternions have in the format is the multiplication has similar schematics to matrices. So you know how you compose matrices? You just multiply them, and if you have two transformation matrices and multiply them together, there's a transformation matrix that is equivalent to doing the transformation of the first matrix followed by the transformation of the second matrix. The same thing works for quaternions. If you have an rotation quaternion multiplied by another rotation quaternion, the resulting quaternion represents an orientation that is the composition of the two individual. Really cool. And yeah, it's very useful. Cool. I hope this inspired you to go look up things I haven't mentioned in Wikipedia. There's a lot more I can talk about. Do the stuff out on the internet. If you have any questions, like I said, email me at AHRS368. There's a lot. So hopefully I've inspired you to go do some research on your own. I'll be sitting around here for a few extra minutes. If you have any questions, thanks. All right, looks like there are no questions. Thanks for listening. See you next week.